All right, how's it going, everybody? We are here on Thursday, February 25th. We're going to hit up section 7.4 today, our sum and difference formulas. Last week, we introduced our ideas associated with trigonometric identities, equations that are true for all values that the variable can possibly take on. And all the ones stated on the screen right here, we got theta as our variable here. Some of the examples that we've seen in the past couple weeks are identities such as cosine is 1 divided by secant. This is a little bit more of a definition rather than an identity here, but it's certainly a statement that's true for all values of theta, but it's true sort of by definition, not by computation so much. We defined secant to be the reciprocal of cosine. The second one that you can see here, sine squared plus cosine squared, each of theta is equal to 1. This is generally true regardless of what the angle is that goes on the inside here. This statement will always be true. This is one of our first identities that we proved this semester. Other identities, like this guy on the right, cosine over sine plus 1 equals 1 minus sine over cosine, is not at all obvious that that's actually true for every value of theta. That's not even true. It's not even obvious that that's true for any value of theta, let alone that that's true for every value of theta. So one of the good things to kind of keep in mind when we talk about our identities here is that in general, the fact that any of these statements is true for all values of theta is not at all directly obvious. What we saw in section 7.3 is that all of our work associated with these is to verify that these are in fact true statements. Because I mean, this just seems, I mean, if you were to just approach me on the street and be like, "Hey Tony, is this true?" I would look at that and I'd say, "I don't know, probably not, but I can check." And if I checked, I would find, in fact, that is actually a true statement right there. But doesn't it's not just I'm not just like looking at that being like, oh yeah, of course, right? Like so the point here is that with a lot of our identities, it's not really obvious that they're true. So a lot of our work that's associated with these is determining statements that are true, right? It takes some effort. It's not just obvious things to us at all. So in these sections here, we're in 7.4 today, and 7.4, 7.5, 7.6, we're going to work to build up a bunch of new identities that we can use. A lot of relationships that are ways that we can take one expression and rewrite it as another expression. One expression that's complicated for another expression that's much simpler. One expression that maybe has a denominator that we don't want to deal with to a different expression that we could actually split up into two fractions. That might be practical for us right there. Right? So today is sort of half about justifying the new formulas or identities that we're getting, and the other half of today is about why do we care to build these? What new pieces of information can we now determine based on the fact that we have these formulas, right? So today we're going to get 6 new formulas, and we're going to get the sum and difference formulas for sine, cosine, and tangent. What we want is different ways that we can rewrite these following expressions right here. So sum and difference formulas, meaning we are taking the sum or the difference of two angles and applying sine, cosine, or tangent to that sum or difference of two angles. What I want to know is there a way that I could write these types of expressions so that I don't have this sum or difference on the inside of my trig function? This just doesn't look like stuff that I generally know how to compute with this sum or difference in here. And so I'm thinking it would be a lot nicer for me if I could write these just in terms of sines and cosines of just alpha and just beta rather than combinations of alpha and beta in there. I want simpler expressions that are going to help me evaluate things that might look like this. So we'd like these to be able to be written just in terms of sines, cosines, tangents of only alpha and beta, like separately, not collectively, like alpha plus beta, alpha minus beta, stuff like that. If we can do that, then you should notice that this is going to give us the ability to come up with exact values of some more trig expressions, things that we weren't in the past able to rewrite, right? I'm noticing things like the fact that sine of 75, I could re-express this as sine of 45 plus 30. And if I write it like this, then now maybe in terms of 45s and 30s, those are angles that I know. And so it seems like it's plausible that we could end up coming up with an exact number that sine of 75 degrees is equal to because of the fact that we know about things like sines and cosines of 45 degrees and of 30 degrees. Very similarly over here for 15, cosine of 15 degrees, it seems to me like I could think of this as the cosine of 45 degrees minus 30 degrees. That is a difference right here. So we could apply a difference formula using values that we are comfortable with, 45 degrees and 30 degrees, to come up with some trig function values of angles that in general we don't consider to be like within our realm of capability. 15 degrees, 75 degrees, they're not angles that we previously have been comfortable with managing. But now it seems like maybe we can, if we can come up with ways to rewrite these sine and cosine and tangent expressions individually in terms of the 45s and the 30s. And these are just two examples right here. Certainly not our like only goal right here. So I want to kind of talk like broadly, like what's our strategy going to be here today. We're trying to come up with 6 formulas today and see how we can apply them. Here's what we're going to do. The first thing we're going to do is we're going to start. Our biggest effort is going to be determine the sum formula for cosine. This isn't like it's the hardest one. It's just that the first one, no matter, I could probably come up with literally any of the 6 formulas first. It's just that the first one is going to take effort because all the remaining 5 are going to be based on the first one that we did. We're going to kind of reuse our old results a lot. So we're first going to determine the sum formula for cosine. That's how we'll start this guy here. Then we'll use our symmetries, our negative angles, so saying things like we know about cosine of negative theta and stuff like that. And that's going to get us our difference formula for cosine. So we'll have sine and cosine, the sum formula and the difference formula. Then we're going to use complementary angles. Complementary angles are the identities that we came up with back in like week 2 that help us rewrite sines in terms of cosines and vice versa without any squared terms on them. So we'll use our previously known complementary angle formulas to help us find the sums and differences for our sine function based on the cosine function. Once we know everything we need to know about sine and everything we need to know about cosine, you should know that that means that we can get information we want to know about tangent by combining our sine and cosine information. We know that tangent sine over cosine, and so we should be able to, once we've got all the sine and cosine stuff, we just got to do some division and we're going to end up with the tangent stuff. So the first one is going to take by far the most work just because we don't have any other previous information to base it off of. Once we just have one of these 6 formulas, we're going to get to keep on reusing components of that to come up with the other one. So all the rest of them will be easier than the first one right here. This first one's the one that's the hardest for sure to come up with right here. So what we're going to want to do here to talk about this cosine of alpha plus beta, where alpha and beta are 2 distinct angles from one another, is we're going to want to draw 2 very careful pictures. I'm going to try to not screw up my pictures right here. I'm going to try and use a little bit of color with these to try and kind of help myself out. So what I'm going to want to do in this diagram right here is I'm going to draw some angles of alpha and beta. And we are looking at this guy as recognizing that we can come up with, wait a minute, are we actually doing... Oh, sorry. We're actually going to be doing our difference formula for cosine here first, right? Isn't that our first one right here? Yeah, I guess we are actually looking at our difference formula here first. I'm gonna change this out right here. I was like, I know what picture I'm drawing, but I'm forgetting what the components actually are made up of right here. So alpha minus beta. So what I'm going to do is just to kind of help myself out, I'm going to picture alpha being a larger angle than beta right here so that when we do the subtraction, we still get a positive number. Right? So what I'm going to do is this. In this first diagram over here, I'm going to draw, this is going to be my alpha angle right here. All right, so we're going to come out to here, and I'm going to mark that first right here. So I'm going to say, there's alpha. Went out to right there. Then we can consider some other angle, and I know I immediately drew that in a place where I need to put another line right here, so I'm going to move that slightly. Here's alpha. Then instead, we're also going to look at another angle right here of beta. And these land at points on the unit circle, right? So here is my beta. And what you can see here is that if we took this amount of rotation that's associated with alpha, and we subtract off the rotation that's associated with beta, then the angle that's in between these 2 lines is exactly our angle alpha minus beta right here. So I'm going to draw that one in color right here so we can see the distinction. So this guy right here then, this should be our angle of alpha minus beta right there. All right. Now, let's label a couple other locations on this graph right here. I want to identify these 2 points because what we're about to do is we're about to draw the same exact picture on the next unit circle, but we're just going to rotate it a little bit. And that's going to be surprisingly helpful here. So what I'm going to do is recognize that this angle right here is our angle alpha, right? That went to that guy there. This just is our angle beta that's right there. Just trying to make sure that we really see what's happening here. So alpha was this large angle that went from the positive x-axis to this guy over here. So this guy opened up alpha, and we know that therefore the location on the unit circle here, the xy location, is exactly the cosine of alpha and the sine of alpha. That's exactly how we kind of measure our location on the unit circle here. So this is cosine of alpha, sine of alpha. That's its xy location, and I'm going to call that point P1. just to name it right here. Similarly, let's name P2 right here. This is based on the angle beta. So the xy location of this point should be cosine, measuring the x value of beta, and sine, measuring the y value associated with beta right there. So there's our point 1 and our point 2 that are going to be associated with these guys. Now what I'm going to do is this. When I go to draw my second picture over here, watch my fingers. All I'm going to do is this. My fingers right now look exactly like our alpha and beta angles, right? So all I'm going to do for our second picture is I'm just going to rotate my hand until this one is pointing on the x-axis right there. So the point is going to be this. The angle between these two is going to remain the exact same. Importantly, the distance between these 2 points must be the exact same. I'm just going to rotate where on the circle they're located. That's the only thing that's really going to change in our upcoming diagram right here. So what I want to kind of do now is say, let's rotate so that the beta angle is on the x-axis. So in that case right there, we should be coming up with, and so I'm seeing here, and visually I'm estimating this is like, I don't know what that, like 35 degrees or something like that. So I should be seeing that we're getting this guy right here, right? That's hitting some point right there. Now the whole point of this is I'm specifically trying to do this so that this amount of angle right here is exactly still that alpha minus beta that we'd previously drawn. What we know is if this amount of alpha, and again, because I just did this, right? So the angle between the two stayed the same because I didn't like move my fingers like this. I kept them just like this. I just rotated them both in unison until that beta was laying on the x-axis there. So what you know is that if the amount of angle that this is alpha minus beta, then this point, which we'll call P3, should be cosine of alpha minus beta, comma, sine of alpha minus beta. And my question is, where is the other points, right? This P3 is like P1 in our other diagram. It's after having gone alpha minus beta degrees of rotation, that's where you landed. Where does the P2 point end up when we rotated? Well, the P2 point ended up right here. And very importantly, we don't need alphas and betas to talk about where that point is located, right? This is just the point 1, 0. So I'm going to call this P4. And it's clearly just 1, 0. So what I want to identify here then is the fact that this straight line distance right here has to still be the exact same straight line distances between these two guys right here. It's got to be, because I just took this shape and just rotated it. Length does not depend on location, right? If I move 2 dots in exactly the exact same way, then the distance between them is always going to be the same. I don't care if I flip them, if I do this, if I do that. The distance between my 2 fingertips is never changing no matter where I move my hands, right? So those 2 green lines are of the same length. All right, so after rotating them, the line from P1 to P2 and the line from P3 to P4 have to be the identical length as one another. I didn't change the length, I just changed where that length was located in space was the only thing that happened. So the really good thing now that we can do for ourselves, let me, oh no, I did get that parenthesis right there. That's okay. So the point is this, I know where these 2 points are located in space. I've got their XY locations. I know where these 2 points are located in space. I know their XY locations. And I know that the distance from P1 to P2 is the same as the distance from P3 to P4. I'm going to be able to set up 2 distance formula statements and set them equal to each other. Let's go ahead and do that. Now, the distance between any 2 points, we can find this with the distance formula here. And notice this is actually just based on the Pythagorean theorem. If we want to know the distance between any 2 points in space, x1, y1, x2, y2, then we can recognize that the x distance that's been traversed right here is x2 minus x1. I'll get some colors in here to make this more easy to see. Right, the width of this triangle right here is you go all the way the length to x2, but subtract off the length out to x1 to leave you with just this length, x2 minus x1. Similar, the height of this triangle is y2 minus y1. What we're interested in is the distance d right there. So it looks like I could make a statement like x2 minus x1 squared plus y2 minus y1 squared equals d squared. What we're interested in is just the positive distance between the 2 points. So we in general write our distance formula as the square root of x2 minus x1 squared plus y2 minus y1 squared. Take the square root of the whole thing. So that distance formula is going to be kind of our key for this guy exactly. So now let's go ahead and do our distance formula between the two, set them equal to each other, see if we can come up with a relationship that's going to help us identify what cosine of alpha minus beta is. That is kind of this is going to be the thing that we're going to see pop out from this guy right here conveniently, right? So let's go ahead and do this guy. So we've got that P1 is cosine alpha, sine alpha, P2 is cosine beta, sine beta. P3 is cosine alpha minus beta, sine alpha minus beta. And P4 was 1, 0, right? I'm just copying down all of these P1, P2, P3, P4 from our diagram up here, right? And what I want to show is that the distance from P1 to P2 is equal to the distance from P3 to P4, and let that kind of be my guiding statement right here. All right, so let's set up our distance formula here. So this distance from P1 to P2, I'm just using our distance formula right here. It looks like it should be the difference in the x values of the 2 points squared plus the difference in the y values of the 2 points squared. And we'll get the square root. So I'm gonna put my square root on after because I know this will be a big expression right here. So this should be my cosine of alpha minus my cosine of beta. Notice that that's the difference of the x values of P1 and P2 squared plus is in my formula, the difference in the y values. Oops. Cosine is not where we get y values. We get y values from the sine function. Sine of alpha minus sine of beta squared. And we take the square root of the entire thing here. On the right-hand side, we get a very similar statement, or structured statement anyway. The x values for P3 and P4 are, it looks like we're going to get cosine of alpha minus beta minus 1. That's the difference in x values between these 2 points squared, plus sine of alpha minus beta. And it looks like this one's minus 0, right? There's nothing exciting happening there. And we can square root the entire thing here. Now, right away, those square roots don't matter. I'm going to square both sides so we can drop the square roots. The other thing that I'm going to see right away is that I think that I want to expand all of these 4 different squared terms right here so that I can see all the parts that I actually have. So I'm going to say square both sides. And expand all binomials. So what am I going to get when I square this thing right here? We've got some of our algebra things that we remember right here. is that x minus y squared is always going to be x squared minus 2xy plus y squared. That's what we get anytime we FOIL out x minus y times x minus y. I'm going to use that as my kind of like guide. That's an algebraic identity right there, that those two things are equal. I should put my equals sign right there. So that's my guiding identity algebraically here. So I'm seeing here that I'm going to get from our first grouping, I'm going to get a cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared of beta. That's my first grouping. My second grouping here is going to be plus sine squared of alpha minus 2 sine alpha sine beta plus sine squared beta. Uh-oh. I don't know if I set myself up for success here with this amount of room. Let me... Okay, there we go. I've gotten a little bit smarter here lately. That's good. Now on my right-hand side over here, looks like I can do... Oop, now I'm going to go back to my black pen. Okay, good. Cosine squared of alpha minus beta. See, minus 2 times x times y. So that's just going to give me minus 2 cosine alpha minus beta. And then on the end, we're going to get a plus 1 squared. That's just 1. And notice our final term over here, that minus 0, I'm just going to ignore it. I'm just getting sine squared of alpha minus beta. Now, this just looks like a giant mess, but there's some really nice simplification that we're going to get to do here. And one of the things that's just sort of slapping me in the face right now is, dang, there are just so many squared trig terms out here. And when I think squared trig terms, the number one thing that I think is the nicest identity that we get, our Pythagorean identity here. That if you add together sine squared plus cosine squared, it does not matter what the term is on the inside as long as it matches. That's literally just 1. So let's see if we can take advantage of that down here. So what I'm seeing here is, I'm seeing a cosine squared alpha, and I'm seeing a sine squared alpha. Those two are just going to join up to be the number 1. I'm also seeing, let's see, I'm seeing a cosine squared beta and a sine squared beta. Those are just going to join up to be 1. Both positive, both sine and cosine squared, both at the same angle. I'm looking out here, and I'm seeing a cosine squared alpha minus beta, a sine squared alpha minus beta. Those are just going to join up to just be 1. That's really, really nice. Like 6 of our terms just turned into 3 1s. It's not going to get much nicer than that. Let's see what else we can do here. Anything else? Not that I'm seeing right now. Cool. Let's see what we end up with here. So, I'm going to want to follow along with my colors here as I've been doing. So maybe I should do, let's get my orange first. Oh, okay, here's what I'm going to do. Okay. Making this harder on myself than I need this to be. So I'm going to get, as my first number, I'm going to get 1 from the orange terms right here. Minus 2 cosine alpha cosine beta. So 1 from the orange terms. I'm looking like I'm also going to get a 1 from my blue terms here. So plus another 1. And then we're going to get a minus 2 sine alpha sine beta. Over here, it looks like we're going to get a, with the magenta, I'm going to get a 1, where that's coming from. Yeah, that's not, is that my magenta? Yes, plum apparently. And a minus 2 cosine alpha minus beta plus 1. And that's just, that 1 came from that guy right there. So here's the thing that I'm noticing now. Now I'm noticing we have a 1 and a 1 for 2, and a 1 and a 1 for 2. So I'm just going to subtract 2 from both sides. Also, I'm noticing that all remaining terms are negative, so I'm going to multiply by everything by a negative 1. And what am I left with here? 2 cosine alpha cosine beta plus 2 sine alpha sine beta equals 2 cosine alpha minus beta. It looks like I just got to divide everything by 2, and I have found a way to rewrite cosine of alpha minus beta. So I'm going to flip this around just because I like to see this guy on the left right here. It looks like we're getting cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Boom. So that took kind of a lot of gross work right there, right? We used several identities, lots of trigonometric ideas right here. But by drawing some pretty careful pictures here and recognizing that two distances were going to have to be equal to each other, but distances that we were representing with different x and y points, especially the x value right here of cosine of alpha minus beta, that's really of interest to us. We're able to use the distance formula, some algebraic identities, and the Pythagorean identities here to combine all this stuff into one nice statement. This is what we would refer to as the difference formula for cosine right here. And now I get to swap all these things right here. So now we can easily modify this to get our sum formula for cosine instead. So let's go ahead and see what we mean with this guy right here, and then we'll do an example. All right, so we've got the cosine of alpha minus beta. So what if instead I chose to have a negative angle for beta right here? Well, then this would really turn into alpha plus some number, right? So all I'm going to do here is say then that cosine of alpha minus negative beta, that's the same thing as cosine of alpha plus beta, should be equal to, in fact, I want to write that on the other side over here just to keep our organization going nicely from left to right. So I guess the point is to say, this is the formula we want. We're recognizing that we can write any addition as a subtraction of a negative right here. We have a formula that handles subtraction between two values, so I just have to use negative beta where I used to have a positive beta in these terms over here. Right? So cosine of alpha, cosine of negative beta now, plus sine of alpha, sine of negative beta. Right? So all I have to know to help myself finish this guy is to say, what's with my symmetry ideas right here? What's cosine of negative beta? What's sine of negative beta? And every time, if I ever forget these, I come back to my unit circle and I ask myself, what's up with the difference between positive angles and negative angles right here? Where if that's positive theta and that's negative theta, then I can clearly see here that sine of negative theta. Well, if I go in the negative theta direction, my y value went negative instead of going positive, but it was by the same amount. So this is going to give me negative sine of theta. And similarly, if I look at cosine of negative theta, well, the two x values of these 2 points are literally the exact same x value there, right? This is giving me x comma y. This is giving me x comma negative y right there. The x values are literally the same thing. So this is just going to give me the same thing as cosine of positive theta right there. That's going to help me with my rewriting right here. So we're going to get cosine of alpha plus beta is equal to What do you give me that spinny wheel for? We're good here. Uh, Cosine. Oh, wait. So cosine of negative beta, that's just going to become cosine of positive beta. I basically just get to drop that negative there. Right? Now over here, though, the sine of negative beta, that's the negative sine of positive beta. So this negative is going to pop out and become a difference between these two here instead. I guess I'm writing these without parentheses. I kind of keep on going back and forth on my parentheses. I don't always use parentheses because I feel like obviously it makes things look way more cluttered, but sometimes things get confusing if you don't do it. So and what I want to kind of draw here is kind of track that this negative is that negative right there. So using our symmetry formulas, we're now able to convert our difference formula for cosine into a sum formula for cosine right here. So now we have our sum and our difference formulas for cosine. So let's do a quick example of seeing how we can use this now. So the cosine of negative 15 degrees, not something that you should know how to do until right now. This is not one of our typical angles that we're used to being able to actually evaluate. But what I'm recognizing here is it seems like I can write cosine of negative 15 degrees. One way that I could write that is the cosine of 30 degrees, which I know about, minus the angle 45 degrees. And now this looks like an expression that I can use my difference formula on. So I'm going to scroll up a smidge so I can see it here. It looks like I'm just following my difference formula now. I'm thinking of this as my alpha minus my beta right here. So it looks like alpha is 30 and like beta is 45. And notice this minus sign is built into the formula for the difference formula. We could use this as the sum formula with alpha and beta, but then you'd need to think of beta as being negative 45 to make that match up. Right? So it looks like how I can write this then, according to my difference formula up here, is cosine of alpha, so that's cosine of 30, times cosine of beta, that's cosine of 45, plus, got a plus in my formula right there, sine of alpha times sine of beta. Sine of 30, sine of 45. And I know all of these values. I know every single one of those four. I don't know what to do with cosine of negative 15, but I know exactly what to do with all four of these values that we landed at right here. So it looks like I can say, so cosine of 30, so when I picture this right here, I'm picturing, I've got my 30 degrees on my unit circle. 30 is this guy right here. I'm picturing that my x amount is larger of the two. So it's the larger of the two between 1/2 and root 3 over 2. So I'm going to get root 3 over 2 here. I know that all my 45s always give me root 2 over 2. I know that 45 degrees is in the first quadrant, so I know it's going to be positive. Plus sine of 30 degrees, the height at 30 degrees is the smaller of the two, so that's the 1/2. And sine of 45 also root 2 over 2. So it looks like I'm getting what, root 6 over 4 plus root 2 over 4. And it looks like my exact answer here is root 6 plus root 2 over 4. I think that this is worth double checking because this just seems kind of crazy to me because this just doesn't seem like an angle that we should have been able to get our hands on right here. So let's go ahead and ask Desmos if it agrees with us right here. So I'm going to pop on over to Desmos here. And we want the cosine of, now I think in Desmos wants me to do radians. So I've got to do, if pi sixths is 30 degrees, then pi twelfths is 15 degrees right there. And we just came up with square root of 6 plus the square root of 2 divided by 4. And we can see that those decimals exactly match each other right there. So Desmos seems to agree with us with the calculation that we just did. But now instead of just getting out some decimal that we don't have any way to interpret or really do meaningful math with, we've got an exact answer rather than a decimal approximation for things like 15 degrees, or in this case, negative 15 degrees. Although what we did learn one moment ago, relearn, I'm assuming, is that the cosine of negative 15 is the exact same thing as cosine of positive 15 right there. So we could have use that idea to help us out there as well, right? But the point is, we now have access to a whole bunch of other angles, all the angles that we could make by doing addition or subtraction between two otherwise known angles. So this is saying from our 30s, 45s, and 60s, we can now get access to any addition or subtraction of 30s, 45s, and 60s as well with our sines and cosines. Or I should say, we've only done our cosines so far. We should now extend and get our sine stuff right here. So let's do one other example right here. And this example is actually going to be really important for how we're going to get our sine information right here. So really importantly with this example right here, it looks like we're going to use our difference formula right here. But importantly, obviously, one of these values is a variable in there. So I'm expecting there to still be theta as a variable in my final expression. But I do know that I can evaluate things like sine and cosine of pi halves. Those are easy. It's going to be 0 and 1 for those values there. So let's go ahead and see if we can use our difference formula. So our difference formula says cosine alpha, cosine, I'm going to label these again. It's our alpha minus beta right there. So cosine alpha times cosine beta was how it starts. Cosine alpha, cosine beta. Cosine of alpha times cosine of beta. Plus sine alpha sine beta. Plus sine alpha sine beta. Our only angle of interest that we got to talk about here is pi halves. I can see that the cosine of pi halves is the x value associated with that point, which is 0. The sine value is the height associated with that point on the unit circle, which is 1. This is just 0 because it's 0 times the number. This is just sine. It seems to me that cosine of pi halves minus theta is just straight up sine theta. This is our complementary angle identity right here, one of them. We actually saw this one out there in week 2, but we haven't directly taken advantage of it for many super useful purposes now. But what you can see is that this is actually going to be a helpful way for us to rewrite sine in terms of cosine. Generally, when I think of exchanging sines and cosines, I think of this formula right here. But this formula is always dependent on us having squared trig terms. And we don't always have squared trig, and we don't want always to have squared trig terms, right? So this is going to be our way to rewrite sines and cosines where we're introducing like a difference term in there, pi halves minus theta, but we now know how to handle differences. So we're fine. It's not really a big deal, right? So let's use this idea to help convert our formula for cosine, or sum formula for cosine, into the sum formula for sine, right? So what I'm going to do is I'm going to think of it like this. I've got sine of alpha minus beta, and I'm thinking of alpha plus beta. So I'm thinking to myself here, I'm thinking of theta as alpha plus beta. Then in that case, it looks like, uh-oh, now what have I done to myself? That means that I should be rewriting this. I'm just following this identity in this slot right here, right? This should be sine is sine, theta is alpha plus beta, cosine is cosine, pi halves remains, minus alpha plus beta. Seems reasonable. The point is, I can now do my sum and difference formula on this guy, right? So now I'm treating pi halves as alpha in green. I'm gonna do a bad thing and overwrite some variables right here. And I'm thinking of this as my beta term right there. It's the first term and the second term, but I'm thinking of this as encompassing this. This is the difference of pi halves and alpha plus beta. Alpha plus beta. That's going to be my 27th Greek letter out there. Alpha plus beta. One word. It's in the second slot right there. That's the important thing. So it looks like we're using the difference formula for cosine to help us evaluate this. So I'm going to remind myself one more time. Difference formula for cosine. Cosine of the first term times cosine of the second term. So that's going to be cosine of the first term times cosine of the second term plus, scrolling back up one more time, plus the sine of the first term times the sine of the second term. Sine of pi halves times the sine of alpha plus beta. Right? And our, hold on, what's my rewriting? I'm okay. Let me show you how I'm setting this up dumb, and let me show you how we're going to slightly fix this guy right here so that this is actually useful to us. The thing that I'm doing that's kind of stupid right here is you should notice that this just went to, and in fact, I'm just going to leave all this and just kind of like, in a sense, fix this. So here, what I'm getting is cosine of pi halves. This is 0, so we're getting 0 from this contribution right here. This is 1, so we're getting sine of alpha plus beta. And it looks like sine of alpha plus beta is equal to, oh my gosh, sine of alpha plus beta. This didn't help. Let's do it the right way. A smarter thing to do is I'm going to take this stuff, and rather than grouping these secondary terms together, the alpha and the beta, I'm going to group up pi halves minus alpha as my first term, and then we're going to let beta be beta over here. That's going to be my new route for this guy right here. Try again. Okay, so sine of alpha plus beta. My first thing I wrote there was fine, equals cosine of pi halves minus alpha plus beta. What I really want to do is write this as cosine of pi halves minus alpha minus beta. And I'm going to group these guys together like this. So now I am thinking of, get out of here. Now I am thinking of the first term as what I'm thinking of as alpha. And the second term is what I'm thinking of as for beta. By now I have by accident memorized my formula for the cosine formula. It should be cosine alpha, cosine beta. So I'm going to get cosine alpha, which here is pi halves minus alpha, times cosine beta, plus sine of pi halves minus alpha, sine of beta. Now, I know that cosine of pi halves minus alpha, based on my complementary formulas right here, this is just the sine of alpha. Similarly, sine of pi halves minus alpha, that's exactly cosine of alpha. That's exactly using the symmetry formulas, exactly those same statements that we just made right there. So I think I keep on saying symmetry formulas. Complementary angle formulas. These angles are complements of one another. They add to 90. Right, these go both ways right there. So that's what I use to make that simplification happen. And we now have our sum formula for sine. And I hope that you are not terribly surprised to see that we're now going to do the exact same maneuver we did before. We did cosine difference, and we used symmetries to get cosine sum. We used complementary angles to get sine sum. We're going to use symmetries to flip it over into the sign difference again. And then we just got to do tangent. We're good. So again, I want to rewrite this difference as a sum. So I'm going to think of this as alpha plus negative beta. And now I'm going to use my sum formula to evaluate it. It should be sine of the first term, which is sine of alpha. It should be cosine of the second term, but that's really cosine of negative beta. But we also know that negatives inside cosines don't matter. For our second grouping here, cosine of the first term, sine of the second term. And we know that sine of negative beta does matter. So just like before, one of these negatives dissipates effectively. The other one, that sine of negative beta, is going to become negative sine of positive beta. So this will again become a difference between these two. Again, I'll draw my little follower line right here. And that is our sine of alpha minus beta. All right. So let's look at a couple examples right here. I'm going to do sort of some forwards in and some backwards in right here. Let's find the exact value of sine of 105 degrees. I'm thinking to myself, I don't directly know sine of 105, but I'm asking myself, does 105 degrees represent the sum or difference of two angles that I am comfortable with? Well, I could think of this a bunch of different ways. I could do this as sine of 135. That's our 45 degree angle in the second quadrant. Minus 30. That's one way we could do this. We could do this as sine of 60 plus 45. That seems like another way we could do this. We could write a whole list of these things that are all going to work out for ourselves. I'm just thinking, how can I break down 105 degrees into two angles that I am more comfortable dealing with? I'm just going to say here, many options. All you've got to do is say to yourself, how do I want to do this right here? I'm thinking to myself, let's go ahead and do a difference formula right here, just for the sake of it. Let's do that first one right there. No real reason why I'm picking that one, just picking it. So what did we learn from our difference formula? The reason I'm picking it is because it's sitting right here. It should be the sine of the first term, cosine of the second term, minus cosine of the first term times the sine of the second term. All we got to know is we've just got to think to ourselves about our unit circle out here. I know that I'm interested in my 30 degrees, and I know that I'm interested in my 135. All right. Again, the 135, that's really one of our 45 degrees, right? It's 90 and then 45 more. So it's going to follow our 45 degree angle values here. So my sine at 135, I can see, I know I'm going to get root 2 over 2. Am I getting positive or negative? Well, it looks like we're pointing up, so we're still going to get a positive value. So this is going to be root 2 over 2. Cosine of 30. Cosine is the longer of the two lengths. The x value is the longer of the two lengths over here. So I'm going to get my larger of my two options. So that's a root 3 over 2. Minus cosine of 135. I know that that's going to be a root 2 over 2. I ask myself, is it positive or negative? Well, that one went to the left, so that's a negative x value right there. And sine of 30 degrees, that's the smaller of the two heights. The y value is the shorter of the two lengths right there. So I'll get my shorter of my two options, 1/2 instead of root 3 over 2. So it looks like my final answer here should be, it looks like I'm getting root 6 over 4 plus, because we have negative and negative, root 2 over 4. Is this the exact same thing as what we got before? Seems like we're getting the exact same answer as the first question that we asked today. And you should notice that that kind of makes sense because I'm gonna say y right here. And actually, can we? So I'm saying we got the same thing as our cosine of negative 15. I'm gonna do this over here. This should be the same thing as cosine of positive 15. And I know that I can swap this guy out for, I'm thinking of this as, actually, you know what? I'm going to leave it. I'm not going to write that like that. And I am thinking to myself, using my complementary angle formulas here, all right, I'm going to come back to these complementary angle formulas. If I have cosine of some angle, it should be the same as sine of 90 minus that angle, right? Well, that's just sine of 90 plus 15. That's sine of 105. Looks like I do know that those should be the same thing by using my complementary angle formula right there. So we get the same answer as the last one, and I can prove that those should be the same because the cosine of negative 15 should be the sine of 90 minus negative 15. That's our complementary angle formula right there, again showing up. So, as our last example, before we go on to tangent things and wrap it up, is let's find the exact value of this expression right here. Now, you should look at this expression and you should definitely say, I don't know what the heck to do with this thing. How am I supposed to know what I would ever get for sine of 3 and for cosine of 87? And this is me yelling at you saying, don't you dare use a decimal in this problem. And you're like, cosine of 3 degrees? Are you kidding me? But what you need to be able to do is you need to look at this and say, you know what? That looks like one of my formulas that I've seen for the sums and differences. Do I expect you to remember which one it is? Not really. I expect you to say, that's an output from a sum and difference formula. Let's go see which one that actually was. So sine cosine plus cosine sine. No, that's got a minus in between. Looks like this one right here. Sine cosine plus cosine sine. Right there is what I'm seeing for sine of alpha plus beta. So it looks like here, so alpha is 3 and beta is 87. It looks like this should just be then equal to sine of 3 plus 87. Well, that's just the sine of 90. It's just 1. Right? So here's a very complicated, difficult expression right there. But it's literally equal to 1 exactly right there. And we know this because we're following along from our sum and difference formulas right there. So recognize that sometimes you'll see some quantities in trig that seem like unbelievable that you should be expected to be able to determine exact values for without a calculator. But in this case right here, just by identifying that this fits the mold of a known identity, you absolutely can kind of rearrange the terms into the other side of the identity. So notice this is in a sense using the identity backwards. Identities don't really have directions, but it's certainly the case that it's much more often that we start with the sign of alpha plus beta and evaluate it with this format right here rather than going backwards. But the point is that this is an equal sign. It's not one directional. You can start with one side and convert to the other side. In this case, it helped us to recombine the alpha and beta to get a nice comfortable angle of 90 right there. So just recognize that when you see stuff that looks anything like this, you should be saying to yourself, I recognize that. That's one of my sum and difference formulas. I know a way I can rewrite that guy that might be helpful to me. And I did that and it was, right? So kind of recognize the structures of these things right here, be able to scan back through and determine what formula it is that's of interest to you. So currently, we have all of our formulas for sine and cosine that we're interested in. All we got to get is our tangent formulas, and that's not going to be that hard at all. You know that tangent is sine divided by cosine. That's all that we're really going to do right here. So let's go ahead and get our formulas for tangent right here. So I want to do tangent of alpha plus beta should be sine of alpha plus beta over cosine of alpha plus beta. I know my formula, the sum formula for sine. I just wrote it right here. Sine alpha cosine beta plus cosine alpha sine beta. Also, I want my cosine sum formula. Let's scroll up and find that guy. Cosine sum, cosine sum, cosine sum formula. Cosine alpha cosine beta. So cosine products minus sine products. And it looks like here we should be able to like simplify this somehow. What I'm really thinking to myself is this. If the sine and cosine formulas all involve sines and cosines, I'm kind of expecting that there should be a nice way to write my tangent formula all in terms of tangents. So I feel like what I want to do here is do some division so that I can convert some of these chunks into tangent expressions right here. So here is what I'm thinking to myself. I'm going to divide this whole expression up here and this whole expression down here by this term right here, cosine alpha, cosine beta. So all four chunks of terms are going to get a cosine alpha, cosine beta dividing them. All right, here's what I'm seeing. Cancel, 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 cancel. No canceling happening over here. But it now seems like I have a good way to write this. Sine alpha over cosine alpha, that's tangent alpha, plus, looks like that's tangent beta, down here, everything canceled, leaving us with 1, minus sine over cosine of alpha, sine over cosine of beta, tangent alpha, tangent beta. All right. So we got 5 of our 6. We're almost there. Let's go ahead and hit this thing with some symmetries and see where we're at. Tangent of alpha minus beta. We're thinking of this as tangent of alpha plus negative beta. So that's going to give me tangent alpha plus tangent negative beta over 1 minus tangent alpha tangent negative beta. Our symmetry here is that tangent follows the same rule as sine. Tangent of negative theta. Oh man. Let me just try writing that all over again. It says tangent of negative theta equals negative tangent of positive theta. So that basically says you pop the negative sign out. So that's going to say to me that tangent of alpha minus beta looks like it's going to be tangent alpha remains. That negative on the inside of tangent, I'm going to pop it out as to make it subtraction between them. All divided by. And here we're getting 1. Tangent alpha remains, but that negative from the tangent of negative beta is going to pop out to join with this negative to make that an addition right there. And it looks like we got our difference formula for tangent. Nice. So I hope that you're learning this theme that so many of these identities are interdependent on one another. If we didn't know about all of our symmetry formulas and all of our complementary angle formulas right here, we would have no way of touching any of this stuff today, right? So we're always using previous identities to build up new ones that help us evaluate expressions that we previously were unable to evaluate here. So some quick little examples for, I think we got 2 tangent examples, and then we got one last kind of tougher example that we'll use to wrap up the day right here. So one example here, we know that tangent is a little bit different than sine and cosine, and that sine and cosine both have a period of 2 pi. It takes 2 pi radians for them to repeat their action. But tangent only has a period of 1 pi because it gets all positives and then all negatives, and then all positives and then all negatives. So it did it twice in 2 pi rotations. It only took 1 pi to get all the way around there. We can express this in terms of some, we could write this using function notation and verify that it's true now using this idea right here. That says we should be able to take tangent of theta plus pi, and that should be giving us the same tangent values as if we just applied it to just theta, right? If you go pi radians further, you should be back in the exact same tangent values as you were before. It's repeating every pi. Let's verify this guy right here. So I can show here that tangent of theta plus pi. Well, I've got my formula up here. And by the way, this is one of those things where I remember memorizing this, I think this was like second semester, junior year of high school. So when I was taking trig as my pre-calculus class before I took Calc 1 my senior year. And I feel like there was like songs that went with like every single one of these to help us memorize them. The one that I remember is this guy right here, goes to the tune of the Mexican hat dance. This is 10A, 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 plus 10B, 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 all over, all over, all over, 1 minus 10A, 10B. And this is like the one where I will never forget this. This is the song I'll be humming to myself on my deathbed, no doubt. So I remember this one right here. So I'm gonna do this here. 10A, 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 plus 10B, 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 all over, all over, all over, 1 minus 10A, 10B. There, we got it here. And we remember that tangent of pi is actually equal to 0 right here, right? Because sine over cosine, sine of pi is 0, and 0 over 1, so we're getting 0. So it looks like I'm getting here tangent of theta plus 0 over 1 minus tangent of theta times 0. Well, that went to 0. That was all 0. That's just equal to tangent of theta, right? So it looks like tangent of theta plus pi, we can prove is the same thing as tangent of theta by using our sum formula for tangent right here, which is cool. Now, one of the buggers that comes up with tangent right here is I'm going to show you kind of like this is one of those like unfortunate things right here, is that sometimes our sum difference formula for tangent doesn't play very nicely. And that's because you need to remember that another major difference between tangent and sine and cosine is that sine and cosine, you can plug in any number that you want. But because tangent equals sine divided by cosine of theta, anywhere that cosine of theta is equal to 0 causes us to divide by 0 in association with tangent, and that means that that value is not in our domain. right? So remember that sine and cosine, you can plug in any number you ever want and it's going to make sense. For tangent, that's not true because we need to make sure we're not dividing by zero. So the reason why the tangent formulas get a little bit funkier is because they have some places where things might not work out, where those things totally would work out if we were in sine and cosine land. So let's go ahead and take a look at this guy right here. So if I try and verify the identity, so this is a true statement, and I might say to you, verify the identity. Well, what you might want to go do is say, okay, I'm going to Mexican hat dance my way to victory here. This should be tangent of theta plus pi halves is what I'm going to work with here. And I'm going to say this is tan A plus tan B, tan B, all over, well, minus tan A, tan B. Right? But this is a problem. It's undefined. Tangent of pi halves is sine of pi halves over cosine of pi halves, which is 1 over 0. Put a big X next to that. Can't divide by 0. So that says to me is it looks like we don't have a way to directly use the sum formula to actually evaluate this. So what do you do when you have tangent stuff and you don't know what to do? Back to sine and cosine. Let's see, how can I rewrite this expression here? Well, I've got my sum formula for sine on top. Let's scan back up and find that guy. There's my sum formula for sine. Sine, cosine, sine with a plus between them. Sine, cosine plus cosine, sine. So sine, cosine plus cosine, sine, all divided by, and notice here, this cosine of pi halves being 0, that's not inherently a problem unless it's the denominator of a function. So I'm getting cosine of pi halves here, but that's not an issue for me. It's a multiplication by 0, which is fine. It's the division by 0 that we introduced that wasn't fine right there. So let's go get our cosine sum formula. It's way up here. Cosine sum formula, cosine minus sine. Cosine minus sine. Cosine minus sine. And now we just need to do some evaluations at pi halves. It's like one of our easiest angles, 90 degrees, right? So again, we're back in this unit circle where our only point of interest is up here at pi halves. So cosine of pi halves, what's our width at that point? It's 0, so that goes to 0. So this whole term went to 0. Sine of pi halves is 1, so we're just going to get cosine of theta down here. Again, cosine of pi halves goes to 0, so that's all 0. Sine of pi halves again is 1, so we're going to get a minus sine of theta. And it looks like we're getting cosine over negative sine, so negative cosine theta over sine theta. Cosine over sine, that's our flipped version of tangent, so that is in fact negative cotangent. So this is just to say there are some tiny roadblocks that you might hit every once in a while. Because tangent has this difference from sine and cosine, right? There are values that are not allowed. Pi halves plus pi k are all the locations at which you're going to run into issues with tangent where you're dividing by 0. Can't do that. But we weren't just straight up stuck on this. This is still a true identity. We're just describing an angle in here. It's not like theta plus pi halves is maybe a bad angle or something. It's an angle. I want to compute the tangent of it. It turns out in this case that because this would turn us into having some tangents of just strictly pi halves, and that's an undefined individual quantity right there, this wasn't a computable number for us right there, or expression. Once we converted into sines and cosines, back in our comfort zone, I just individually used the sum formulas for sine and for cosine to get a clean expression for this, and we were able to verify the identity that we did get tangent of theta plus pi halves to look like negative cotangent of theta by applying the sum and difference formula, not for sum, but for sine, or not for tangent, but for sine and for cosine. Cool. So, last example of the day right here. One that's a little bit tougher, and we want to kind of be careful with this guy. We're going to bring back in our inverse functions right here, right? So, for this guy here, what we want to remind ourselves is exactly what we learned in 7.1, which is regular trig functions take in angles. Therefore, inverse trig functions must spit out angles. So cosine inverse of a half, that's some angle. And actually, you know that one. So you should stop and say to yourself, wait, what's cosine inverse of a half? Because 1/2 is something that we normally do get out from cosine right there, right? However, sine inverse of 3/5, that's not one that I know. I don't know what to do with that. So here's what I'm thinking to myself. I want to do is decompose this into the two things that I think that I see it to be right here, right? So I'm going to say to myself, let's call this alpha, and let's call this beta. I'm going to just remind you, angles come out of inverse trig functions. So all I'm doing is giving some arbitrary name to what that angle is, right? I don't know it. I'm just calling it something. I'm giving it a name so I can deal with it. So this is going to lead me to is alpha is what I'm calling cosine inverse of 1/2. I'm going to apply cosine to both sides and say cosine of alpha is 1/2. Similarly over here, I'm going to say beta is sine inverse of 3/5. And I'm going to take the sine on both sides to say sine of beta is just 3/5. So what I'm thinking to myself then, and I'm going to, by the way, I'm going to leave some room because I know what's coming right here. So I'm going to leave myself a little gap right here. And I'm going to say that this expression right here, I should be able to rewrite as sine of alpha plus beta. And therefore what I know is it seems like I can use my sum formula for sine, right? And I think we did that right here. So I'm going to follow this one. Sine of a sum, sine cosine plus cosine sine. Sine cosine plus cosine sine. So it seems to me like if I knew both the sine and cosine of alpha and the cosine and sine of beta, then we'd be good. All right, I changed my mind. I'm not going to do this kind of dumb layout right here. I'm gonna move that stuff back up here so that my work is in the physical order in which I'm doing it here. What? There we go. Back to this guy. So I've got cosine of alpha and I've got sine of beta. I just need to get the others from them, right? So let's pause for a moment and let's compute what the others must be. So this is like us saying to ourselves, if you know cosine of alpha, can you get sine of alpha? And the way that I think to myself to do this is to draw the triangle. I know that cosine is, oh, come on, I just got so hopeful today that I could do all this in half the space. I don't know what I am thinking. Cosine of alpha, here's my triangle. Here's my alpha. And this should be, cosine is adjacent over hypotenuse. So that's 1, that's 2, So therefore, this guy right here it should be 1 squared plus blank squared is 2 squared. 2 squared is going to be 4, and that's 1. So this has got to be a square root of 3. You actually knew this because cosine of alpha being 1/2 means that alpha is going to have to be, and actually I drew this thing pretty bad right here, but it should be 60 degrees is what this guy should be right there. But we don't even know this one over here, right? So if I do sine of beta, that's 3/5. Sine is opposite over hypotenuse. This one actually takes a little bit of math right here. X squared plus 3 squared equals 5 squared. X squared plus 9 equals 25. Subtract 9 from both sides, we get 16. And so x is apparently 4. So this is a 3, 4, 5 triangle, it looks like that we're working with right here. And the point is now, I now have triangles for alpha and beta, so I can get exactly the values that I need for myself right here. So I think I can go ahead and get this guy now. And by the way, notice we're never even finding alpha and beta. We're just figuring out if you know the sine of alpha, can you get the cosine of alpha? And the answer is yes. You just draw your triangle to get all your relationships here. So sine of alpha plus beta is equal to sine of alpha. I'm just copying down the line from above. All right. So it looks like I'm getting here sine of alpha. Do I already know that one? No, I knew cosine of alpha. Sine of alpha should be opposite over hypotenuse. That's root 3 over 2. Cosine of beta. Cosine of beta, did I know that one? That was the other one I didn't know. Cosine of beta should be 4 over 5, it looks like here. Plus cosine alpha, that was given to me in the problem. I don't even need to look at my triangle. It's sitting right there. Sine of beta, or I shouldn't say it was given to me in the problem. That's a thing I defined for myself. I defined the sine inverse and the cosine inverse as alpha and beta right there. Right? Similarly, sine of beta was what I defined it to be. It's 3/5 right there. Awesome. So we have come up with our expression for this guy now. For our sine of, what was this sine of? Cosine inverse of a half. Plus sine inverse of 3/5 is equal to. It looks like we're getting, I don't really want to cancel because I guess I want to keep my common denominator of 10 here. So I'm going to say 4 root 3 plus 3 over 10. Seems like a crazy and gross answer, but again, I want to encourage you that you can check these guys in Desmos. So I just got a couple concluding thoughts here and we will call it a day. One concluding thought. When you see inverse trig functions composed with other things, you should stop and say to yourself this statement. Angles are what come out of inverse trig functions. And so you should name that angle in like most all cases. That's our useful thing to do is say, when you see an inverse trig function wrapped up in some other stuff, name the inverse trig function and angle. Theta, alpha, beta, phi, name it something so that you can work with it. Right? The other lesson that I'm seeing right here is you should expect to see some moderately gross answers like this, and you should expect that you can still check them in Desmos. So let's go do this. I'm going to throw this guy into Desmos here. And when I go to Desmos here, I am looking at sine of cosine inverse of a half. Sine of cosine inverse of 1/2. By the way, it's telling us root 3 over 2 right now, but I'm not done. Sine inverse of 3/5. And it's giving us some 0.9928. We got an answer a moment ago of, come on, help me wrap it up here, 4 root 3 plus 3 over 10. Let's see. 4 root 3 plus 3 over 10. 4 root 3 plus 3 over 10. And there we go. So you can still, even though I will always expect you to be giving me exact answers and not decimals for these, you can still verify that the exact answer that you came up with must be correct by kind of checking that the decimal expansions, the decimal approximations are equal to each other right there. So it helps me feel really good about the answer that we got right there. All right, so my final thought for the day is this. Final thought for the day is you should be checking out the back of your trig textbook. And I'm going to show you exactly what I mean right here. I've got this guy already brought up for us right here. If you go look in the very back of your trig textbook, and I think I've brought this up before, I just kind of want to show you that this is covering like literally the entirety of our class right here. You can kind of see our whole course in one page when you go look at this thing right here. And I kind of want to show you exactly where we're at. So this is just a scan, a PDF of that back page of your trig textbook right there. Let me do this. There we go. And now slide me over a little bit. Boom. So this is the back page of your trig textbook right here. And you should see, this is all on one page. This is our entire semester on a page right here. We started the semester by defining sine, cosine, tangent, cosecant, secant, cotangent, all based on a triangle. Then we said for any general angle, not just in a right triangle, we should be able to maintain these relationships. So notice this angle is bigger than any one that could be in a right triangle. So this was like late chapter 6. Then we got into our trig identities, which is where we're at now. We know that tangent is sine over cosine. This is all of our reciprocal relationships are right here. We got all three of our Pythagorean identities right here. We've got all those even-odd identities of how do you handle negatives on the insides of your trig functions right here. We've covered all that stuff. Today, we got all 6 of our sum and difference formulas. So here's the 6 formulas that we just came up here today in 7.4. Tomorrow, our next video in 7.5, we're going to get our half angle and our double angle formulas. Notice the one little special thing about this. It looks like there's 3 different useful double angle formulas for cosine right there. That's a little weird and a little special. This thing comes up. I swear to God, in teaching Calc 2 and differential equations this semester, I have had to use this formula right here. I have used that formula, I'm not joking you, like 15 different times in the last 3 weeks. These things keep coming up all the time in your calculus classes. All the time we need rewritings for these things. So this is going to be section 7.5. That's our next video this week. This is going to be section 7.6, our product sum and some of the product formulas, and that's going to wrap up our identities for chapter 7. Then 7.7 and 7.8, we go on to equation solving. There's no new identities that we get out here. Then when we get into chapter 8, hold on, let me make sure I'm not talking wrong here. For our chapter 8 things right here, for our chapter 8, we're going to get law of sines and law of cosines, and that's basically going to give us everything that we're going to want to have known about triangles right here. This is the bottom of the page right here. So there still is some other content that we cover in this class that goes kind of beyond that, but you can kind of see that like this was chapter 6, this was chapter 6. Here we are in 7.4, we got 7.5, we got 7.6, we've got 8.2, and we've got 8.3. So like all these things are kind of consecutively coming up. This back page of your textbook right here is really, 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 really useful to you. And when all of you guys go take calculus next semester or the semester after that, holy cow, you're going to have forgotten pretty much all of these formulas, but you're going to need to use them all. And so what really matters is that you have a good reference source for all these things right here. So it matters not that you memorize all of these, but that you generically recognize them, know that they exist, know that you can use them if you look up the appropriate formula right here. So this is like my single most used piece of reference material in all of teaching as a college professor is the trig insert from the textbook right here. This is the stuff where I have memorized maybe half of this page. And I'm a math professor teaching trigonometry, using it constantly in calculus classes. And I have memorized, gosh, I forget the exact structure of these all the time. I never remember how these ones go. I mostly remember these, but like I'm dependent on like singing a song and stuff like that. And I definitely remember these, and I will care that you remember those as well. But like the point is, you're not supposed to just be memorizing lists of stuff. You're supposed to recognize general structures, know where your reference information is, and be able to use your reference material successfully. So this is a page that's like worth you having as a separate thing. You should take a picture of it, and this is like, fold it up and keep it in your wallet with you for the rest of your life for the next time that you need a trig identity kind of thing out there. You're gonna want this page right here. So yes, be aware of this in the back of the book. I like that it's a guide really for 3/4 of our semester essentially is what we're looking at just on this page right here. So good stuff back here. And so it's good for us to kind of be able to see where we're at. This right-hand column right here, these are our next 2 sections. These bottom things down here, they'll happen in 8.2 and in 8.3. So I will see you guys, and let me see here, next video, section 7.5, double and half angle formulas. It's going to feel a lot like today, except that the hard part of today was doing our very first one, and we've got that out of the way. So what we're going to see for our half and double angle identities is just like today's 5 out of 6 of them. They're all based on previously determined ones. We had to do difficult work to get our first formula here today. That was hard. And then our other 5 formulas followed from it. All the rest of the identities that we're going to get are just going to be us doing swoopty round rearrangements of stuff that we've already got. So we shouldn't have any difficult work like that very first derivation that we had today. All the rest of these are just like, can we put together old identities that we already know to come up with new useful identities? And the answer is just going to keep on being yes, right? So that's what we got for 7.5 in our next video, and then 7.6 next week. That means that next week we're also starting equation solving, and then we're going to keep going. There's 2 sections of equation solving because it can get kind of hard, and there's kind of a lot of cases that we want to cover. So it's 2 sections for a very good reason out there. It's the goal, the culminating goal of chapter 7 here. So it's really important. It matters that it's across 2 sections. So I will see you guys for section 7.5 on double and half angle formulas in the next video. Have a good one, everybody.